Today, I'd like to introduce a topic which hopefully I'm kind of knowledgeable about, given that I've been doing this for about 5 years of my life as of the time of this recording. Let's get into the introduction to plasma material interaction. So I am Mark Jeffrey D. De Leon, currently an assistant professor in the Department of Mining, Metallurgical, and Materials Engineering. Before we delve into plasma material interaction, we must first define what plasma is. So simply put, plasma is ionized gas, and in this ionization event, plasma becomes a quasi-neutral mixture of ions, electrons, neutrals, radicals, photons, and heat. Plasma, we take gas particles, we add energy to them in the form of radiation or electricity. In order to produce charged particles, our ions and our electrons. So this event is what we call ionization, and this is what turns your gas particles or gas phase into the plasma phase. As in all phase changes, meron din tayong reverse reaction, which we call your recombination. Recombination is when your ions and electrons recombine in order to produce your gas particles. In normal conditions, your recombination is more favored than ionization. To sustain our plasma in Earth, we want to have a balance on the ionization and recombination events in our system such that there is always some ions or some plasma that is existing in our system. In materials field, we study plasma since plasma can interact with the surface of our materials in a process which we call plasma treatment in order to modify the properties of these surfaces. So the avenues in which plasma treatment can occur can be through deposition, etching, implantation, plasma activation, and so on and so forth. So shown here is a typical plasma reactor. So this is something that we use in the Plasma Material Interactions Laboratory housed in the Department of Mining, Metallurgical, and Materials Engineering of UP Diliman. Current plasma treatment process. First, we have your plasma deposition. In plasma deposition, we're simply adding material onto the surface of our substrate. So there are two avenues for plasma deposition. We have your sputtering, in which a target material is impacted by ions, dislodging your target material, then being deposited onto our substrate. We also have plasma-enhanced chemical vapor deposition, in which we're ionizing our materials to be deposited. So yung material in the deposit natin, this is in gaseous phase. By ionizing this will then react with your surface, creating a thin film of a material. So PECVD and plasma deposition process in general is very important in terms of creating thin films. So these thin films may act in order to either improve the hardness or the tribological properties, or even imparted with special properties such as antimicrobial or antibacterial properties, depending na lang sa application natin. Next, we have your plasma etching. In plasma etching, we are removing material from the surface by impacting ions and other particles onto the surface of your material. See? Natanggal siya. So plasma etching is especially useful in processes such as plasma cleaning. Plasma cleaning is a process in which we are cleaning the substrate or our surface of impurities by the action of plasma. So in this case, in the bottom right, this is HDPE contaminated silicon. Then after 6 minutes of plasma treatment, you can see there is a significant reduction in the HDPE or high density polyethylene contamination of the surface. Your ion implantation. So ion implantation happens when we impart our plasma with a lot of energy. Since your plasma is highly energetic, this allows it enough energy to penetrate your material, implanting it inside of our material. This is especially useful in the production of integrated circuit since this is the primary method in which we create our dope regions, yung mga P and N regions natin in our silicon. This is a preferred method over your diffusion-based implantation since this creates doped regions which have better depth control. We can actually program kung gaano kalalim yung pupunta ng ions natin. And it is also more anisotropic than your diffusion-based systems. And this is especially important since in very, very small devices, we need that much control. Interaction of your plasma and our material, the modification of the material surface would happen. So this can be illustrated in the tuning of our polymer surfaces using different plasma treatments. So first we have PMMA. Upon the plasma treatment of PMMA using helium and argon plasma, we see that there is an improvement in the hydrophilicity. So mas nagiging hydrophilic or lumiliit yung contact angle ng water onto our PMMA surface. We can also use plasma to turn our surfaces hydrophobic, such as in the case of silicone rubber. So in this study, what they did was they cleaned the surface of your silicone rubber to create a more hydrophobic surface. So plasma and materials, when they interact, there's a lot of different possible interactions, only some of which will be tackled in this lecture. How plasma and our material surface interact, we now look at how we can produce our plasma discharge. In 1889, the Paschen's law was established, linking the breakdown voltage or the voltage needed to create plasma in a parallel plate system with the pressure of your environment. So in this case, what they found is that by decreasing the pressure from atmospheric pressure, we are lowering the breakdown voltage or essentially the energy needed to create our plasma. So this is the case because recall, in the production of plasma, we have two competing events. You have your ionization and recombination events. So as we lower the pressure of our system, what we're doing is we're essentially increasing the distance between our ions and our electrons, thus making it less probable for these two to recombine to go back into gas, thus sustaining our plasma longer. So in the case of the 13.56 MHz RF plasma etcher shown on the right, we actually need a pressure of around 100 pascals or about 1/10,000 or 1/1000 of atmospheric pressure. Due to this low amount of pressure, your traditional artificial plasmas need vacuum conditions to be generated, which will mean we'll need vacuum pumps. Traditional plasma technology requires the use of vacuum systems to be generated. This makes your process expensive. It also slows down the treatment time, or it slows down the treatment since we need to wait for our pressure to go down to a suitable amount. And it also limits the applicability of your plasma treatment since marami tayong constraints such as the cost, the material that we can treat, the throughput, and so on. So one plasma systems, the biggest of which is the need or the necessity for vacuum systems. There is now a new or relatively new development which we call your cold atmospheric pressure plasmas. So from the name, it is cold, it's non-thermal, and also more importantly, it does not need vacuum systems to operate or to treat our surfaces. So this enables the cheap, simple treatment of your surface since tinanggalin natin yung vacuum component. And this also increases the applicability of your treatment since now we can treat even those vacuum-sensitive surfaces. So with this development, our cold atmospheric pressure plasmas, into atmospheric conditions, we can now explore more novel uses for plasma, one of which is your plasma sterilization. So in plasma sterilization, we're deactivating or we're killing microbes, bacteria, viruses off the surfaces of our material. So an example is the inactivation of our fungal spores. So in this case, we use microwave argon oxygen plasma to kill fungal spores in our petri dish. Use your plasma in agriculture. So we can use this in the treatment of water, in the treatment of seeds, or in the treatment of the soil. And this could be useful in the increasing the production of food in the future. So with that, I'm done with this short lecture. So hopefully may napulit naman kayo. And I'll see you next time. Thank you for listening.